Okay, good evening, everyone. Today, we continue our discussion on a new topic, which is linear programming. Basically, we try to learn some concepts that related to either maximizing or minimizing some certain mathematical functions. Let me show you on the board. Unfortunately, your friends over Zoom, I don't think they can hear, and I try to.
Professor, we can hear you.
Yeah, you can hear me, but I want to show something on the board. I don't think you can see. So, do you guys see it here? Yeah, you should see. So, let's say this is booster. And I have a cargo company here, or I'm a postman. Let's say I'm a postman. I have some parcel that I should send it to, let's say, Shrewsbury. Southampton, Hopkins, Lower, in Boston, you should visit all those cities. Send your products.
Sorry.
All those cities. What can you do? One could be you go here, and then go to Hopkins, come to Shrewsbury, go to Boston, go to Lowell, Hopkins, here. It's a way of sending your products on from Worcester to New York, all the cities up to New York, right? Is there any problem with this solution? So what's your problem? Yeah, if you just ran zigzagging there, you just wasted too much of labor and gas price. Yeah, actually, this is a good answer. So maybe one of the good solution, not necessarily the best one, with Worcester, Shrewsbury, Boston, Hopkins, Lowell, here. It seems more efficient. It may not be the best solution, some might be better. So basically, in LP and operation research in general, we try to find the optimum solution. That's the only goal. So how we need to find some mathematical equation. So if you want to, maybe you can by eyeballing and based on experience you can solve it, but you cannot tell a computer and just look at the board and just find the best solution. So you need to convert that figure to something computer friendly. So you need to code it in the way that your computer can solve the answer. So this is the goal of this section. It may or may not be your future job, but whenever you end up almost in any businesses, there is so many people do operation management. So you either are as MBA, Antics, Finance, you need to collaborate with them. So if they talk about they want to optimize their work, you should understand what they're talking about. What do they mean that I want to have an efficient way of distribution? Any questions? So you understand the goal of the next few sessions, hopefully. So we already passed one homework due, so but the next project delivery is in 3 days. If you want to change the topic to what Efrat presented last class, and if you want to use his data, you can submit by October 30. And then also, in case it's your interest, I suggest, and you want to work in the healthcare industry, I think it's a good topic to work with. At least you can get prepared for his next presentation, and you can do basically a part of your project and just present the class. But you don't have to change. It's just an option for the people who wants to work on Efrat's data that he presented on in the last class. Let's see. Also, you may need to have Microsoft Excel ready because we do some operation management problems, and we do over linear programming. So you need to have solver in the Excel ready to be able to do that. So have Microsoft Excel on your system. So, but just as a recap, so in the previous classes, we did some hands-on experiences in sentiment analysis, association rule mining, and we had basically some transaction data, and based on transaction data, we try to understand some association rule between items that we have. Okay, excluded this assignment, so it's not your assignment. Okay, so today we have a little bit of focus on graphical linear programming, like what I just showed to you. So you try to basically have some visual grasp on the problem that you are going to solve. But later on, the next few classes, you would see it's almost impossible for the real case problems when you have too many variables. But at least with graphical solution, you can figure out and understand the concept that is behind of that is under hood of this algorithm. Okay, so as I said, the goal is using mathematical equation and converting this visualization to something that your computer can solve. So your computer cannot do eyeballing. So we need to have some reviews on algebra, and later on we use our algebra knowledge to be able to solve linear programming problems. So also, if you never had linear programming in your previous classes, I recommend to come to the class because I might use your whiteboard a lot. In case you haven't had this concept before, it might be a little challenging for you. Okay, so can anyone answer the solution? Can anyone find A and B? I think it's very straightforward. So no worries, it's a new concept, but it's not very scary. So you just find B based on A and then substitute in the next equation, and you can easily find the solution. How about this one? Is it the same? Okay, sorry. Yeah, it's the same. So let's draw it. So we said that today we are focusing on some graphical linear programming. So let's draw on a 2D dimension, and either through drawing you can understand what is going on. So when you want to draw on piece of paper, so maybe your X could be A, your Y could be B, and you draw a line, or vice versa. Your B could be X, A could be Y. So here A is X axis. So if you want to draw the line, one time you would say, what if my A would be 0, so B equal 20? So the the line that represents 2a plus b equal b intersects the b axis with the value of 20 and intersect a axis with the value of 10. Any questions so far? We are just reviewing some maybe high school mathematics, so no worries. I mean, later you find the association of these equations with the linear program. So if you intersect that two lines, you can find the solution. So basically the solution of this equation is the point that intersects that two lines, a plus b equal 15 and 2a plus b equal 20. And this is the answer. Isn't it a straightforward way? Okay. So now we want to make it more realistic. So, and as Amarildo said, if you want to use the first transportation plan, it may not be efficient. So let's focus on the first transportation plan. So your truck gas tank has a limitation. So maybe at how many gallons? Maybe 20, 40? I think 40 or 50 gallons. So you cannot put more gas. So just keep in mind, your gas has an upper limit, let's say less or equal 50. You don't have a full tank. Maybe because of your problem, you have to, but there's a cap. So you would say the cap for the truck tank is 50 gallons. So in real case scenarios, usually we don't have something equal something. Usually we have a cap. We would say something less or equal or more or greater than something. Same for here. So what if I change the problem to inequality? So 2 times a plus b less or equal 20. A plus b greater or equal 15. For example, I just know what, because I just had a discussion with him, I know which business is active, is working in. So if next time you come to my office hours, so I can understand what you guys, what you do in your, what you did in your life. So yes, let's say you want to sell some bed sheets. So one of the stores requires you to deliver at least 20 bed sheets per week. So some of the inequalities could be greater than something because you have maybe because of you have a contract with the store, you should at least deliver 20 bed sheets in a week. Okay, let's plot it. So for 2 times a plus b less or equal 20. So look at the left figure. When you say less or equal something, we are referring to an area, right? So the feasible area or the area that works, do you think it's in the left side of the line or in the right side of the line? Yeah. Yeah, you're right. So if it's hard to visualize in your mind, maybe you just throw a number, 0 and 0. So a equals 0, b equals 0. The summation is less than 20, right? So this is here. Or 5 and 5. A equals 5, b equals 5. Both of them are here. So basically, this is the region that works in the first one, right? What about a plus b greater or equal 15? Could I plug 5 and 5? No. But what if 15 and 20? Yeah, for sure it's more greater or equal 15. So sometimes it's easy to visualize it, like here, but sometimes if it's hard, you can just find some random number in the one side, and you can find what is the associated region. Okay, hyperosm. Okay, so if you want to change your topic to what Efrat said, so just submit the second one, but for your final project delivery, you need to include something the first submission to. But for the next submission, you just need to submit the second delivery. You don't have to submit the first one. Okay, let me try to use my board again. Last time when I wanted to try, it was a lot of noises. I couldn't do that, so let me just do it again. Okay, can you hear me properly? Oh, you cannot hear me. That's weird. Let's see. Oh yeah, your friend can hear me now. Let's try to use my board.
We can hear you, Professor, now.
Okay. So you can hear me now too, right?
We can hear you now.
Okay, so we just talked about graphical approach for linear programming, and we just have two non-equality, and we found the associated region. But what if we have both of the condition together? We want to find the area, the first works for this equation, also works for this one too. So therefore, the region should overlap both regions. So it would be, so if you overlap these two together, the common part works for both inequalities. So this would be this region, because based on the first one, this was my feasible region. In the second one, this was my feasible region. And if you overlap them together, this blue part would be the common part. We call it feasible region. It just means there is a region or area that works in all of the non-equalities. It just means that. And what we do today, but early in the class, I talk about transportation problem, but it also has so many applications in manufacturing, especially in manufacturing. You might have some limitations like labor, your budget, your delivery constraint, like. But in general speaking, our life is limited. For example, oil in the earth is limited, land, time, money. We have limited resources. We want to get the most from our resources. So this is the general goal of the problems that we are going to cover in this course. Yeah, I mean, Elon Musk wants to screw this course, I guess. But oil is just on the earth. I don't think you can find oil. Oil is just dinosaur juice. Maybe they can find hydrogen, but oil, I'm not sure. That's interesting. So just keep in mind, sometimes, I mean, it doesn't mean if you make good decision, you end up having good outcomes. Maybe you try to minimize the disaster. Maybe at the end you make a good decision, but doesn't, like, you're just minimizing a disaster. Anyway, so we would learn some structured modeling approach for decision making that helps us to make better decisions. And what I mean better decision, we try to have the best decision, but sometimes your problem is so complicated, you are not necessarily, you cannot necessarily find the best solution. I'll talk about them. Okay, so let's talk about a little of dictionary of this concept. I mean, dictionary of linear programming. So we have three major terms: decisions. So let's say, as our first example, you want to minimize your distance. You don't want to just go randomly. Constraints, I think we just talked about that. An objective for transportation problem might be minimizing the cost. For even for manufacturing, maybe you could maximize the output. You name it. So anything that, for most of the decision in your life, you try to maximize basically your goals or minimize your costs. Don't freak out, but this is what you learn at the end of this course. So first of all, we have some decision variables. We call it x1, x2, up to xn. So for example, how much x1 could be how much gas you take. X2 to be how much you pay for workers. X3 could be how much time you have. So you just have basically, you decide about your resources. So min or max function. So you either try to maximize your profit or minimize your cost. It just doesn't mean. And we subject to some resource limitation, for example, oil, time, budget. So we showed our resource limitation after subject to. But no worries, after like few sessions, it just makes a lot of sense. Here, right now might be a little challenging. Like this problem. Okay, let's try to solve a problem. From this session, I try to show you some famous linear programming problems. So there's unlimited number of or types of problem, but there's some major ones. So next time you see something new based on your previous similar problems, you can solve a new problem that people showed to you. Okay, so Blue Ridge hot tubs produces two types of hot tubs: aqua spas and hydroluxes. So aqua spa requires one pump, 9 hours of labor, 12 feet of tubing, and the unit profit is $350. Hydrolux, it still just needs one pump, 6 hours of labor, 16 feet of tubing, and $300 of unit profit. So if you sell the second one, you make $300. If you sell the first one, you make $350. Maybe intuitively you would say, let's just make aqua spa, so it seems we make more profit. But if you have limited resources or if you have unlimited resources and unlimited demand, it's the best option just selling aqua spa. But in real life scenarios, we have limitation in terms of number of pumps, labor, tubing. So these are the limitations that we might have. So first of all, we just have 200 pumps, so we cannot sell more than 200. In terms of labor, you have 1566 hours of labor. So, and 2880 feet of tubing available. So at least here, you can think of objective function. So is a manufacturing problem? Usually in these cases, the objective function maximizing your profit. So what about decision variables? What would be our decision? Decision about what here? Now this is the objective function, but you decide on how many hot tubs you want to produce. Very good answer. Yeah, these are your decision variables. And you subject to some resource limitation, which is like number of pumps, number of hours of labor, and feet of tubing. You are very right. So let's, instead of writing a sentence saying number of aqua spas to produce is one of my decision variables, let's name it X1. And number of hydroluxes to produce, X2. Our objective function is maximizing our profit. So let's say if you be able to produce 10x1, which is the number of aqua spas to produce, look at the previous one, the profit 350. So if you produce 10 of it, your 350 times 10, 3,500. What about number of hydroluxes to produce? So your profit is 300. Let's say if you make 10, you make $3,000. So, So the last one is my objective function. Based on the decision that I make about my decision variables, I end up having different profits. Okay, let me wait a little bit if you can think about it, and then I go to the next part. So your friend over Zoom, if they have questions, they can ask you. Just wait 1 minute. So by the way, do I teach too fast or slow? Is it acceptable? Okay, thank you. Okay, let me go back to the problem again. So my cap for hours of labor is 1566. What if my first decision variable, which is about aqua spas, I decide 10 of them? So it means, so it takes 9 hours. I decided to produce 10 of it. 10 times 9, 90. So 90 would be deducted from my hours cap. So you deduct 90 from 5066. So what if my decision variable for Hydrolux would be 10 of it, or let's call it X2 from. So we just said this one is X2, this one is X1. So if I decide 10 X2, how many fits would be taken from my resource? 160, yeah, 160 feet would be taken from your tubing resources. So let's just put all of them together. So first one is about number of your pumps. So your cap is 200. Let's say if you make 150 X1, you cannot produce more than 50 of X2. Same for labor. So the first one takes 9 hours, the second one 6 hours. So this, based on what your decision, you end up you shouldn't consume or take more than the available hours of labor. And same for tubing. The first one takes 12 feet of tubing. The second one, 16. So those coefficient of 12 and 16 comes from how much would take if you just make one of it. And it doesn't make sense if you say X1, X2 less than 0. Doesn't mean negative aqua spot. Doesn't make sense. So you also said X1 and X2 greater than equal 0. Any questions so far? So I hope the equation makes sense for you. So we have the first, let me just review again. So first you decide what your decision about. So you find your decision variable. Then you want to see what was your goal, how you, so your objective function is maximizing based on the profit times the decision variables value. Also, you know that you have some limitations for resources. Let's put all of them together. Although you see so much of equations and like notations, but it shouldn't be scary for you right now, right? So the first one, let me change the color to objective function. And then resources. So just look the evolution. First, it was some write-ups. Then we figure out how to write or how to translate it to mathematical equations. The goal is just let computer to solve it for you. So if you put these sentences in your computer, cannot understand what you're talking about, but you can put number and equation in Excel. You have seen some similar cases that you put numbers and you crunch numbers in Excel and you can find the answer. So the goal was just converting some narratives to some equivalent mathematical equations. So if you end up working in a company, let's say, I'm pretty sure FedEx, Walmart, Amazon, all of them try to minimize the cost. So you might end up being an analytical department. People just show you some operational research equation. It shouldn't be freaky. you know, those people learn how to solve them by hand and how mathematically prove them, but it's not practical. Even them, they just put in the software and they find the optimal solution. But I mean, the goal of the next few sessions is for you to be able to communicate with those people. Even you can make some very complicated problems too, because we don't go under the hood of these equations. Under the hood of them is really complex. So we want to first translate the narrative to mathematical equivalence, then just put in a software, get the answer. So this is a two-dimensional problem. We just have two decision variables. So still we can use a piece of paper. But let's say instead of x1, x2, I have x3, 4, 5, 6. It would be like 5 dimensions. In those cases, we cannot draw it. But the first class, let's just draw it and graphically solve the problem. When it gets more complicated, no human can imagine. You just try to translate to mathematical equivalent, then just put in the software. But you just need to know what each part of those equations, what does it mean? So when people talk about resources or like objective function, what they are referred to. First part, similar to this problem. So you have seen here, instead of having equation, I have non-equational relationship. So we try to find feasible region. Here I just have two equations. Based on them, I found the feasible region. Now I have 4. So exactly the same thing. We just need to overlap those regions and find the common. Okay, the first one is a pump constraint. So with x1 plus x2 equal to 200, and let's say if you make x1 0, you can find when it intersects x2, and if you make x2 0, you can find when basically intersects the x1. So you can make that line. Then you should decide but you know this is a pump. For pump, your cap is 200. So it's basically less. The region, the associated region, is less or equal to 100. And you just need to know, is it left side or right side? I think for this problem, it's very easy. You can understand left side should be less or equal to 200. But if you just hard to imagine for you, you can just find a random number. For example, if I just put 100, so x2 is 0, x1 is 100. So there's a 1 point on the left side that works in that non-equality. Also, we have labor constraint. So you first use the equation to draw the line, then you know that is less or equal 1566. Then you overlap the first two regions. So first region was everything here, less than this line. For the second equation, it still is less than here and here. But these two parts don't overlap with the first non-equality and second non-equality, right? We just, it doesn't work. So we need a region that works in all non-equalities. So although the second boundary may cover more points, like here, let me just erase this one so I don't want to confuse you guys. Oh. For some reason, my eraser doesn't work. That's bad. Anyway, so I think you found the idea. You know the idea. So we draw the line of each equations and then find the overlap parts. Same for the boundary of tubing constraint. So the first one takes 12 feet, the second one 16, and the cap is less or equal to 2880. We cannot just use more tubing. Again, we intersect all of those regions that we had so far. So the blue line, let's say the blue area is our feasible region. It's the region that overlaps in all the constraints. For example, this red one, this red region doesn't overlap with the other two regions, or this one, the green one, it might work with this non-equality and this non-equality, but it doesn't work for this one. So we didn't use this. You look it as white. So because again, the feasible region just means work. It should work in all those regions. Any questions so far? So can you again explain what does feasible region means? Right, yes. Okay, so now we have feasible region. This is the region that works in all of the non-equalities that I had. But just keep in mind, we have objective function based on the decision variables that you have. So how many first hot tubs you produce or how many second one, you might have different objective function. The most intuitive value of objective function is 0. So if you don't produce anything, your profit is 0. So let's say this point. You can't see that. Okay, let me just change the color. It just means you make 100 of x1 and you don't produce anything of x2. So x2 would be 0, x1 350 times 100. And you can just plug other numbers that are that are located in your feasible region. But look, first it was here 0. Then when I moved here, or basically, let me just put it somewhere here. So when I just move my objective function line to the right, it seems it increases my objective function value, right? In the most left side, it was 0. But when I'm moving to the right side, the value is increasing. So what you guess? What do you think? What is the maximum value? What would be my maximum possible value for my objective function? Probably the rightest point, right? So anyone could guess what could be from line 0.1, 0.2, 0.3, 0.4. So these are the rightest points. Some of you might say 3. Some of you might say 2. Or maybe even 4. But for sure, 1 doesn't seem to be. So what can you do? Basically, the most intuitive way that makes your life much easier, you just look at the corners of your feasible region and just plug all of them. So for sure, your maximum point should be in one of the corners. It cannot be an internal point. Because any internal point, for any internal point, there is another point in the right side. So you don't have to check everything inside the feasible region, because if you find any point within the feasible region, still there is one point in its right side. And you already know if you move your objective function to the right, you are just maximizing its value, or you are increasing its value. Maybe it's hard to guess what could be, but it should be either one of your corners in the right side. So even you can just try 1, 2, 3, 4, all of them. So it makes your life easier. So after finding your feasible region, you don't have to just eyeballing how to move your objective function and find the best solution. You just plug your corners and see what would be the best value. Any questions? So even here, we have a two-dimensional problem. It's very easy for us to imagine and see if you should move your objective function line from left to right, it increases your objective function value. It's pretty much easy, right? It's easy to imagine. But let's say instead of x1, x2, you have x1, x2, 3, 4, 5, x6. So in those cases, it's very hard you cannot imagine six-dimensional problem. Even for those cases, still you can find the corners and just plug in your objective function. So for 2 dimensions, maybe it seems very naive, but when you have actual larger scale problems, you can just find the corners and plug in your objective function, and you find the answer. Same here. Here, maybe with eyeballing, you can find the best corner. By the way, the best answer that either maximize your objective function here, or our goal was maximizing the profit. So, but in the first problem, it was minimizing the distance. So anyway, the best solution has a name. We call it optimal solution. So these are just how to intersect those lines. Okay, let's have a summary. So we have seen that many real case scenarios, your goal of business is usually for business to maximize the profit, or in some application, maybe minimizing the cost. And sometimes it's very intuitive. For example, the first transportation problem, Amarildo could easily say, okay, maybe if you go here and there, it's easier. But let's say instead of like 6 or 5 cities there, you have 200 cities. It's really hard to imagine. Let's say how FedEx do that, or USPS does that, or like Amazon, how they send the products. So Amazon try to minimize the prime time, so the time that they send products to you. They do this problem every day. So they try to minimize their transportation time and cost. In those cases, you cannot eyeball and there is no one in the transportation center of Amazon that eyeballing, okay, send this truck here. That is almost impossible. You have too many customers, and it's not feasible. So that solution is canceled. So it's very hard. It's almost, let's say it's impossible to do a real case or business cases and solve them with the eyeballing. So you need to use computer. But how? You need to convert your problem narrative to equivalent mathematics, which we easily did it for for hot tub problem. So we end up having a feasible region, and we had objective function. And even that time, we tried to eyeballing and see if, okay, if I move to the left side, it seems like I'm decreasing my objective function, which is not good because I want to maximize profit. If I move to the right side, it seems like I'm maximizing my optimal solution. So, but the computer cannot do eyeballing. So the way that the software does, or your friend who are doing operation management, industrial engineering, how they do, basically, they find some mathematical way of doing that. But in the summary, everyone tries to look at the corners. Even your computer has a very advanced internal mathematics. But at the end, your computer just look for the corners of feasible region and find the best solution. But under hood is so many complex things that even in the real case scenario, I'm pretty sure in Amazon, they just use the software to maximize or minimize the cost, maximize the profit. So nobody can have time in the business, real case industry problems to look for inside the feasible region. It might be some funny cases, like look at here. Here we change the feasible region. Both this point and this point have maximizing our objective function. Here the problem is different. I'm not talking about the hot tub problem. Let's say this line is my objective function line. I move it from left to right. In the most right part, it just exactly overlaps with my edge of my feasible region. So these two corners are rightest points. So I have maximum values, so both of them are optimal. Two parts of a line has optimum answer or maximum in a new problem I'm talking about here. Both of them has the optimal solution. Since two end of a line has the optimum answer, all the points in this line has the optimum solution. In previous case, you just have one point as optimal solution, but here you have unlimited number, too many, infinite number of optimal solutions. It could happen sometimes. Basically, in that case, slope of your objective function and the slope of one of the basically feasible region edges exactly overlap each other. So if it's my objective function, this line, so which is one of my edges, and objective function has exact same slope. So when I move to the right to maximize it, I find unlimited or infinite number of optimal solutions. It could sometimes happen. So if somebody tell you you have infinite answers for your objective function, it just means your slope of your objective function or overlap with one of the edges of your feasible region. Basically, just if two of your two corners has exactly same answer, it just means everything between that two corners has same solution.
So, does it mean that both the equations itself are the same? It just means that the slope is equal.
Look at this. Again, I'm talking about new problems. Let's say the association between labor pump and tubing is different. I'm not talking about same problem, exactly, totally new, brand new problem. Look at this line. It seems redundant because for making your feasible region, you just need this one and this line. So 2 lines is enough, or 2 constraints is enough. So in these cases, we have redundant constraint. So here I'm talking about the language of this domain. So sometimes if say we have infinite answer, you should understand what they are talking about. Or if they said we have a redundant constraint, you just keep in mind what does it mean. Let's look at the total new problem. So in this one, my feasible region is unbounded. Let's say for this one, I say less or equal. For another constraint, I say more. So my feasible region doesn't have a cap. It's just an unbounded problem. So in that case, let's say this is my objective function. So when I move my objective function to the right to find the value that maximizes my objective function, it never stops, it just goes forever. Because I can't just move it to right. There is no cap, there is no, basically it's not bounded. So we call it an unbounded solution. Usually when they try to define the constraint, they make some mistakes. It usually happens because in real case scenarios, in nature, it just doesn't make sense. You cannot maximize your profit forever. So usually you should have a cap. Look at this one. Let's say for the first constraint, you're saying I'm looking at this line and more than that. For the second constraint is less or equal. These 2 constraints never overlap each other. So we have an infeasible problem. Still, it usually comes, it could happen. Some cases you have such a constraint you cannot satisfy. So this one could be because of a mistake. The second one could possibly, sometimes you cannot satisfy all the constraints. So we say we have infeasibility. We don't have a feasible region to then look at the maximization or minimization of objective function. Yes? I have these 2 constraints, and I make this constraint. And both of them are saying that greater or equal. This one is redundant. So anyway, infeasibility just means you cannot satisfy all the constraints. There is no solution. In this case, how many solutions I might have? Yeah. In one way, you can say there's infinite answers. You just can maximize whatever. It doesn't make sense, but mathematically, it just goes forever. In this case, we have unlimited alternative options. Because every point on that line has exactly the same answer. Because my objective function, one of the edges of feasible region exactly overlap with each other. So no worries. Later on in the next classes, I solve some problems. When you use a software, it might say, okay, there is no feasible answer. So you need to know. So when you see in the software that error, you should understand what the software is talking about. So if it said we have abundant solution, just keep in what does it mean. So basically today, when I show you these figures, I just wanted you guys to know the dictionary or the language of this domain. So because later on we use some softwares to solve the problem. Basically on all of those softwares, they try to find the corner and then plug those corners into objective function and tell you what is the optimal solution, either the maximum point or minimum point. Any question? Okay, so in next few classes, we might have some exercises with Excel and Lingo. So if you don't have Excel, that's even okay. I think everybody should have it, but I show you how to solve these problems in Microsoft Excel, which is a very common one. Also, we use Lingo. Lingo is a free one too. So if you use Mac, you can use Lingo too. But we have some exercises that we do with Microsoft Excel and more specifically, solver extension. So there's an extension in the Excel, they call it solver. Then also we work with Lingo, which makes your life even much easier. I don't see any questions or raised hands. So by the way, what's your feedback about the linear program? Does it seem complicated, easy, or just okay?
Very, very complicated, Professor.
Okay, thanks for your comments. So yeah, you should come to the class. So if you stay at home and look over Zoom, it might be complicated. Cool. Thank you.
I'll be coming to the class.
Okay, cool. See you next time then. Thank you very much. Take care, guys. Bye.
Thank you so much, Professor.